Hello, welcome to Engineers Ireland. Today we're going to talk about the ellipse. Now, I know that almost all of you will be saying the ellipse is not on the Leaving Cert. It actually is, it's just not covered in the textbooks. Part B of paper 2 has 4 questions in it. The first one, question 8, is the one that almost everybody uses as their special question. They even refer to it as a special question, and we've covered it. Now, what we're going to do is look at question 11. Question 11 has 2 things, one of which is the ellipse, and the other is a bit more on the transformation side of things. And many of the transformations will be applied to solving particular problems in relation to the ellipse. The reason I'm covering it is to give you guys a choice in part B, just in case question 8 is difficult. Now, to begin with, what we'll do is introduce the ellipse through a discussion on the locus. You've come across the locus before. It's in 2 chapters. You have it in the geometry of the line, and again, you have it in geometry of the circle. And we'll just give you a quick example to show you where it comes from. In both chapters it tells you how you deal with it is you define a point, any point, and we do our usual thing. We name it and we'll call it xy. The point P is xy, x comma y. And this point is looking to belong to an exclusive club, and the exclusive club is defined by a rule. What you've seen in the circle and in the line so far is that we could have 2 points, A and B. And we're now going to look at some point, and we'll say P. And we're going to wonder if this point here belongs to a particular club. What we have seen before is that the length A to P is equal to some constant times the length P across to B. What you will have seen in geometry of the line is that when K equals 1, the locus, which is this special club, when K is an element of R, but not equal to 1, any other value, we're basically saying you will get a circle. And that's how the game played out. What we're now going to look at is another search for an exclusive club. But the difference is that we're going to have a line which has a name called Directrix. And you can obviously then call that D. And it has a point, which is generally called a focus, and you can call that F. And we're looking for points that will fulfill the situation of the length. And we're now saying, what lengths are we going to talk about? That length, P to F. And it's going to be equal to some constant times, and we'll say the distance from a point to a line. Well, means perpendicular distance, and we can call that point over here Q. It's the next one after P. This time, the constant itself has a special name. It's called eccentricity. And it's normally called E. So we will, instead of calling K here, we'll put in an E. Other than that, we're facing the same kind of problem that you have experience in already. If we had a different point, we could call the first one P1 now and the second one P2. The same rule has to apply. The distance from P to the point, which we are calling F for focus, must be equal to the exact same constant multiplied by its perpendicular distance to the directrix. Now, when E equals 1, you get a locus, that is a parabola. What's a parabola? It's basically the quadratic equations you've been using for at least 5 years. When E is greater than 1, you get a locus that is a parabola. And that's not something you've seen before. It looks a lot like a parabola. It's shaped a lot like it. Now the bit that we're going to focus on, because it's the bit that's on the Leaving Cert, is when E is less than 1. You get an ellipse. That's going to be our bit. This value will be smaller than 1. It's important to remember this, because in the last 6 years, the part of the question that related to the ellipse actually started back at that fundamental relationship. All of this stuff, by the way, started way back in Greek times with the study of conics. And just because I happen to like to remember and pay tribute to the people who actually did the early work on this, I'll give you the name of a guy who was heavily associated with it. Apollonius of Perga, about 200 BC. So these things were being studied 2¼ millennia ago. And they found some really interesting pieces of information in relation to the ellipse, the circle, the parabola, the hyperbola, and conics. And conics, if you think about it, cone in conics, we'll just, for example, draw the type of thing that they were dealing with. You can imagine that that's a cone. And this here is a sister cone. any of these lines that runs down through the system, and we'll just pick one of the ones that's on the edge here. But even if we pick that as a line, we could imagine that to be just a rod. And if we rotated it around this centre here, it'll swing out and cause that cone. So all lines, straight lines down on the surface of this that go through the centre, and this centre is called the vertex. All of these lines are called generators. They're called generators because one line, any of those lines, can generate the cone. I'm not going to go into any further detail in relation to how you can get an ellipse, a circle, a parabola, or hyperbola here. I just want you to know that what we'll be looking at started 2,250 years ago on a study of straight, a simple plane cutting through this shape. We can set up our points in such a fashion as to make our equations easier. Now, what I'm going to cover now isn't even the specialized little part of ellipses that you're covering in the Leaving Cert, but I'm doing it to step you in so that you can see where things come from. We can construct our problem in a particular way. We can put our origin here, and we'll say that the directrix D is the y-axis. This is clearly the x-axis. And we're going to look at our focus. And we're saying it's going to be a certain distance along. Because it's on the x-axis, the y bit is nothing. So we're saying it's k all the way across. From here to here is k units. Now let's pick a point. And we're going to start asking questions about this point. Just xy. And again, we will go Q here. Now look at the point Q. We know P is x, y. And on the y-axis, x has value of 0. So you can see constructing it with the directrix on the y-axis is going to make our numbers easy, and putting this line here, which is the primary axis, the main axis, major, along the x-axis. We're saying the major axis of whatever shape we'll get now is along the x-axis. We're saying doing that just makes our numbers easy. And we're going, I know that this is E times Q of P. And I'm in a very happy position because I can actually work out what each of these things are. This is the distance between 2 points. And going all the way from Q to P. That's the length x, which we're taking to be positive here. So we can say that implies that equation will either give you a parabola, a hyperbola, or an ellipse, all depending on the value of e. When e is less than 1. Now, that is us having looked at the basics, okay? The little bit that we've covered now, you don't need to learn it off for the leaving, but it's just, we're saying, how do we get down to an ellipse? How is it that these locus problems can lead us to a solution set, an exclusive club, that's going to turn out to look like this thing. Now you'll have to forgive me for not having the ability to draw a better ellipse than that. The easiest way to know what an ellipse is, if you, for example, have a standard cylindrical glass anywhere, or basically any glass that has a round top, a circular top. If you looked straight down at it, you see a circle. But if you look at it from the side like this, okay, you don't see a circle. You see that it doesn't seem to be as high in this direction as it's long here. The shape you're looking at, which is a circle from an angle, from not straight down, that's an ellipse. This is my poor approximation. Now we're going to start talking about the bits that are on the Leaving Cert, okay? The Leaving Cert deals with central ellipse. That means it's going to be centered at the origin. Now, we have the largest axis, which is the major axis, happens to be running along on the x-axis here. Sometimes the ellipse will have the largest one running along the y, and we'll come to see how that can happen now in a minute. Now, what we're basically saying to ourselves is that the focus that we talked about, this F guy, I'll start with this one. The vertex, which is normally called A. If the vertex is the distance 5, we're saying A is 5. The focus is A multiplied by E, the eccentricity, and nothing up or down on the Y because it's on the x-axis. What about our directrix sitting over here? The equation of any vertical line is x equal to some constant or another. And the constant for this so that point there is A over E. So that whole vertex is x equal to A over E. The interesting thing about the ellipse is that it's completely symmetric. So you actually have mirroring it, so the right hand side way over on this side. You have a second directrix, which we can call D dash. You have second focus, and you have this guy, A dash. Now, the name we give to the height of it is B. So the y value here is b, so clearly down here the y value is minus b. What else do you need to know? The general equation for a central ellipse. Where a squared is greater than b squared. You will see in the diagram here that is the major axis, it's the bigger axis. This one here is the minor one. Because it's the minor one, the ends of the minor one are always called b and minus b. This is if the ellipse has its major axis along the x-axis. Okay? However, you get x squared over b squared plus y squared over a squared equal to 1 if major on the y-axis. Okay. The only difference is the bigger one is always called a. So in these equations you'll have the a squared. And once you name it that way, you can figure out everything. You can figure out the coordinates of the focus, the equation of the directrix, the eccentricity. Now, let's pick this one because this is generally how it's written. And it just means that the major axis is on or lies across the x-axis. How else can we write this? Because there's a new little bit coming in here. Now, by the way, if you remember the big equation that we had a few minutes ago, the general one that came out from the locus, which was the distance between 2 points and the distance to a line, you can use that equation to work and prove your way through all of these things. But it's not on the leaving. And all I'm trying to do is to step you into these bits, which are on the leaving. What you will notice here is this is telling us that b squared is equal to the a squared outside of 1 minus e squared. Okay? This is a very important little equation. Now, the easiest thing to do at this stage is to pick a problem. You have basically all you need here. I've just rewritten this so I can clear the lower half here. X squared over 25 plus y squared over 9 equals 1. That's an ellipse. Interestingly enough, if instead of a plus, if that was a minus in here, that would be a hyperbola. So we know once we've got the plus in here, we're okay. Now then, one of the things you can notice from this is if up on this equation, up on the diagram here, if b happened to be the same length as a, what you would have from this, we'll just pull it over here to talk about it, you would have x squared, we'll just say a squared is 25, and we'll just say that b squared happened to be the same value. That'll give us x squared plus y squared equals 25. So you have a circle. Once b is the same size as a, it's just that special form of an ellipse, which is a circle. So the first thing we have to do is check that number 25 is bigger than 9. So we're going to use this version of the ellipse equation, not the one that would have put b squared under the x and a squared under the y. Now life gets very easy because this diagram and this equation here will let you solve all the things you need. This question is going to ask Well, it's certainly asking more than you would normally get asked in the Leaving Cert, because this normally comes in as a part A, or it'll come in into part B. The second part of the equation of the question 11 has to do with the transformations, and we'll cover that the next day. So, what are we asked to find? Find the vertices. That's these outside points here. We want to find those two. The foci, and foci is the plural of focus. We're talking about, over in the diagram, you're talking about that and that point. The directrices in the diagram, we're looking for the equation of that line and the equation of this line. Okay? We want the eccentricity. And we can also get the length . The major plus minor axes. Sorry about this being all stuck together, but I'm just trying to put it on the one page so that we don't lose track of the diagram and you still have your equations. So we're going to find vertices, foci, directrices, eccentricity, and the length of the major axis and the minor axis. This thing here, all the way from minus A across to plus A, is the major axis, and clearly, because it's smaller, going from B down to minus B is the minor axis. What does this equation do for us? That implies that A squared equals 25, which implies A equals, and you don't have to worry about plus or minus, A is 5. And the reason for it is, it's over on this, the right-hand side in the x-axis, right-hand side of 0, and the minus 1 is over here. So we'll say A is 5 and A dashed is minus 5. That's that guy over here. Also, means that B squared is equal to 9. That implies that B is going to be equal to 3 and B dashed, this guy down here, is equal to minus 3. Now we can do the easiest ones first, the major and the minor axes. Major axis, goes from minus A all the way across to A. So it's equal to 5 plus 5, which is equal to 10 units. Minor axis goes from minus B across to B, which is equal to twice the B value. Now you couldn't call that difficult. At least not without laughing. So we have now got that bit done and that bit done. Okay, what's the next thing we can do on this? We're going to find the eccentricity using this equation over here. we know that b squared equals a squared outside of 1 minus e squared. So 9 is equal to 25 outside of 1 minus e squared. And that implies e is equal to 4 over 5. Now, that's an easy equation to work out. So we get e is 4 over 5. Eccentricity is always positive, okay? Because it's a ratio of two lengths. You can't have a negative ratio of two lengths. So that's why, even though we get an e squared equal to something in this equation, you only go for the plus answer. If we look at the diagram again, and we concentrate on the focus, this guy here, we know the focus F is equal to A by E, and A is 5. You're going to multiply it by 4 over 5, so the focus is 4, and that implies the second one, the one over on the left, is minus 4. So that'll be minus 4, that's 4. The directrix D, the one over on the right hand side, it's equal to A divided by E, so it's equal to 5 divided by 4 over 5, which is 25 over 4. That's D. Also, the D dash, which is that line back here, so you'd call D dashed here, it's equal to minus 25 over 4. Once we have found out the value of A, that value 5, that will tell us what our vertex was. So we know that the vertex, because we're dealing with a centered ellipse, we're going to have 5, 0, because the major axis runs along the x1, and the other one, this was the vertex A, the A dashed one, is minus 5, 0. This is junior cert mathematics. However, it is relating to a very important shape, that of an ellipse. Now, basically everything you're going to get that I can see anyway, having looked at quite a number of years past papers, in relation to the geometry of the ellipse, we've covered already. Now, we started by talking about the locus, and it gave a little bit of revision into the locus for the line and the circle, which has to do with the special club formed on relationships of lengths between 2 points. And then that easily stepped us into saying, well, hang on, if one of those, instead of being a point, was a line, what happens? The locus you will get then can fall into 3 different shapes. If the ratio between the lengths is 1, in other words, they're equal, you get a parabola, and that's basically just a quadratic equation. If the distance from the point to members of this club is bigger than the distance from points on the club, in other words on the shape, across to the straight line, you get a hyperbola. The one we have for the Leaving Cert is where the distance from the point, which we're now going to be calling a focus, to any point P in our solution set, if that distance is less than the distance from the point, perpendicular distance across to the line, you have an ellipse. One of these things here that would look prettier than I've drawn, obviously. And they're the basic pieces of information you need to know about them. That the focus, if the major axis along the x-axis, the focus is A by the eccentricity, that's the ratio of the two lengths, that's the x value. the vertex is just A, and the directrix has the equation x equal to A over E. If, as this problem was showing us here, if that big number, you see it's bigger than the 9, if that big number was underneath the y squared, we would have written our equation not like this one here. You'd have written it with the A underneath the y squared, and you'd have gone through the exact same process here, because we'd know then that the ellipse would look like this rather than like that. Now that you've been introduced to the ellipse, you will find the next day, when we're dealing with transformations as they appear in question 11, you'll find that a lot of them relate to ellipses and special properties of ellipses. Just before I go, I wanted to mention one other thing to you about these guys. Just in case you want to, or it comes up. If I pick any point on an ellipse and I look at its distance to one of the foci, and also its distance to the other one, when I add those two lengths, that length and that length together, I find a constant. And that constant is equal to the major axis. Okay? Just in case you get curious for more information, another very odd relationship about them is the tangent at any point on an ellipse happens to have exactly the same angle between the contact point of the tangent and each of the two foci. See it here. That angle between the tangent and this focus line down here is identical to the other one. They're just pieces of information to keep in your head. But it does make for very interesting results if you move on and you learn a bit more on ellipses. Well, I'll let you go at that. And you know that we do wish you well in your Leaving Cert, and we're almost finished here. So I'd hope that by getting in a question 11 for you, that we will open up a possibility that you have a choice in your part B, and therefore we'll be able to remove some of the concern that you might have coming up to the exam. Okay? Bye now.